Welcome back to our series on Introductory Statistics. I'm Mark Ledbetter. We're going to cover Chapter 7, Section 6, and this is Part 2. So in the last video, we discussed how we are going to use the normal distribution to approximate the binomial distribution. Now, why would we do that? Well, if you remember, the PMF, or the probability function for the binomial, is n factorial over, well, we're going to use R here. The book uses R, so I will use R. I believe it does. N factorial divided by R factorial and n minus R factorial. Then we have p to the r, q to the n minus r, r equals 0, 1, up to n. If you remember, this is not a fun distribution to calculate manually unless you love math like I do. But in any case, when you get very large numbers of n, you really don't want to use this binomial distribution to find the probabilities unless you have a computer. So let's use an example, or let's complete an example where n is 20 and p is 0.4, and we want to find the probability that x is greater than or equal to 10. So the first thing that we need to do is check our requirements. And so to check our requirements, we need n times p. We're given n, we're given p, so that's going to be 20 times 0.4, which is 8. That is bigger, equal to or bigger than 5, so we're fine there. Now we need to do n times q. Remember that q is 1 minus p, so if p is 0.4, q has to be 0.6, and 0.6 times 20 is 12, and that also meets our requirement of at least 5. So I could say greater than or equal to 5, greater than or equal to 5, so we can use the normal approximation. So we need the mean and we need the standard deviation. Remember that this is mu here. So one of the things that we have to calculate in order to understand the requirements is the mean. And the mean is going to be 8. And the standard deviation is always the square root of n times p times q, which in this case we're going to approximate as 2.19. So we can use two decimal places, use the number of decimal places specified in the WebAssign or in your book or in the worksheets that I've provided. All right. So the probability that x is greater than or equal to 10 is the same thing as the probability that x is greater than 9.5. So this is a continuity correction. We had greater than or equal to, so what we want to do is come over here to the number line. And this is what we're looking for, this line here. So 10, it's greater than or equal to 10. I have a solid dot there going upwards. It's greater than, so we go to the right. Well, we'll never use the value in that we're looking for. Whatever this value is, we never use it. We use a value either above or below it. That is the continuity correction. We're either going to subtract 0.5 or we're going to add 0.5 to this value. All right? So which do we need to do? Well, we're going to have to move either to 10.5 or to 9.5. So which way should we move? If we move up to 10.5, then we'll be missing the probability. We'll be missing this probability here. Okay? So we don't want to do that. So we're not going to move up to 10.5, or we'll exclude that from our probability calculation. So instead, we don't move up to 10.5 in this case. We need to move down to 9.5 and say greater than 9.5. We don't want to say equals to, although it wouldn't change anything here. Technically, this is the same. These are the same two numbers under the binomial. The probability that x is greater than or equal to 10 is the probability that x is equal to 10, 11, all the way up to 20 in this case, because n is 20. And this is the same thing. There is no probability for the binomial between 9.5 and 10. So these are two of the same expressions. They are both true for the binomial. They would not be the same when we convert them to the normal. If you remember, the normal distribution is continuous, so there is no probability at the equals, which is why we have to move this. So if we have greater than or equal to, we subtract. .5. And so we're going to calculate the probability that x is greater than 0.5. And this is approximately, these two things are exactly equal to each other. This is approximately equal to, and I'm not going to count off if you're a little sloppy here and just say equals to, that's fine in this course. But we're going to take 9.5, we're going to use z. So z is equal to x minus mu over sigma. So now we're changing x to z, and we're going to subtract the mean, which is 8, from 9.5, and then divide by the standard deviation, which is 2.19 from up here. And when we do this, we get the probability that z is greater than 0.68, rounding to 2 decimal places. So make sure that you can get this correct. Please practice this on your calculator. Make sure you understand how to round correctly to 2 decimal places. Well, this is a greater than sign, and that is not in our table. Our table only contains the less than, or less than or equal to. In order to get this probability that we're greater than, we take and we subtract that probability. We subtract from 1 the probability that z is less than that number. Okay, so 1 minus the probability that z is less than 0.68, and that will give us the probability that z is greater than 0.68. And so when we look up 0.68 in our z table, we find that the value is 0.7517. Subtracting that from 1 gives us 0.2483. And if we go to the binomial table and add up all the probabilities for x's 10, 11, 12, all the way up through 20, we get 0.239. And so the approximation is a pretty good approximation here. Now, we just want to find the probability that x is greater than 10, not greater than or equal to 10. Well, it's helpful for me to draw a number line and use the correct notation. Greater than 10 means that I have an open circle here, so I do not include that. Remember that there is no probability between 10 and 11, but especially not between there and 10.5. So if I use greater than or equal to 10.5, it's going to be the same as this is exactly equal to the probability that x is greater than 10. And whether I use a greater than or equal to or just a greater than really doesn't matter in either the binomial or in the normal, because for the binomial there's no probability at 10.5, only at 10 or 11, and in the normal there's no probability at any point. Okay, so I do like to be consistent. If this is greater than, then I like to use greater than or equal to here. And then I need to convert that to a z-score. So we subtract the mean, which is 8, divide by the standard deviation, 2.19, and that gives us a z of greater than 1.14. Again, we won't find that in our table. We'll have to say 1 minus the probability that z is less than that number, and that will give us 0.1721. Now the actual here is not as good. This is not as good of an approximation. The further we move away from the mean, the less the approximation is, the less accurate the approximation is, I guess I should say. So the actual here is 0.122. So there's a 0.05 is a difference, and so for whatever reason this is not as good as our earlier less than or equal to. Okay. Now let's do another. Let's find the probability that x is less than 12. So again, less than 12, we have this open circle here at 12, and we're going to move 0.5 away from 12. So we're going to actually go down to 11.5. If we went to 12.5, then we would include the probability across 12, and we don't want that because this is strictly less than 12. So that tells us we need to move less than 12 down to 11.5. So we need to subtract 0.5 in this case. Okay? And so this makes it the probability that x is less than or equal to 11.5. We convert, so we could continue to do that and find the probability. I'm not going to do that. I just wanted to give you the starting point because, again, we're going to do the same thing. We're going to take this minus the mean, which is 8, and then divide by the standard deviation, which is 2.19. If I wanted to find the probability that x is less than or equal to 12, I would have to go up to 12.5. So I have to add 0.5 to this because I need to include 12, and I have to move a half away. Which way do I move? I have to go above 1/2 in order to go, because this is less than, I need to move above it so that I include the probability of 12. Okay? So here are the rules for the continuity correction. I've given you the actual rules. A and B are just constants. So if it's the x is less than a, then we make it x less than, and we subtract 0.5 from a. If it's less than or equal to, we add 0.5 to a. If it's greater than b, then we add 0.5 to b. If it's greater than or equal to b, we subtract 0.5 from b. If we have 2 equals to here, if we have the x is between the two values a and b, and we have an equals to, then this we subtract 0.5, this we add 0.5. And I've worked out each of the specific cases so you have all possibilities here. So this sign is what's controlling what we do here and here. Okay? So these directions are controlled by which sign we have in these places. All right. Now, so those are the continuity corrections. I hope that you will write these all down on your formula sheet so that you can easily get to them. We'll pick up here for the next video. All right. So that's it for this video. Hope you enjoyed it, and I hope you will take care of yourself, stay safe, because we hope to see you here next time.